Okay, so if we have a look at this graph of atomic radius, the first thing we need to note, I'm just going to pick a colour here that's going to stand out, is we have on our x-axis here, I'll make this a little bit thinner, we have our atomic number, which if you remember essentially is a number of protons, okay, in the nucleus. And so here we have 0 protons, and as we further to the right that we go, we get more and more protons added to the nucleus. And then the y-axis, which is over on this side here, we have our atomic radius. So atomic radius, which if you remember, is the distance from the nucleus to the valence electron. So if I actually draw this, I'll do an example here. This is our nucleus. Let's say this is hydrogen, there's only one proton, and there's one valence electron here. This distance between the nucleus and the valence electron is our atomic radius. So in other words, it's how big the atom is, right? If that distance is really large, it means you've got a huge atom, and if it's really small, like in the case of hydrogen, it means you have a small atom. So as we go back up here and we start to look at the graph, we have hydrogen here, this is helium, and then we jump all the way up here to lithium. So first of all, let's just see what's going on from hydrogen to helium. So hydrogen has an atomic number of 1, okay, meaning hydrogen has 1 proton. Helium, on the other hand, has an atomic number of 2. So we have 2 protons. So what we're doing is, as we go from hydrogen to helium, we're increasing the number of protons in the nucleus. So instead of this situation here, let's call this hydrogen. With helium, make my nucleus a little bit bigger, seeing as we have, this is just 1 proton. And for helium, I'll draw in a second, we have 2 protons. Actually, let me make that a little bit smaller. 1 valence electron, 2 valence electron. This is helium, and here we have 2 protons. This distance here, this atomic radius for helium, is smaller than it is for hydrogen. If you look at the graph here, the atomic radius for hydrogen is approximately what? Here it's just over 50 picometers, and for helium, it's almost, I mean, it's very small, okay? We're getting close to what, maybe 10 picometers or so. And if you look at what's happening, we have added 1 additional proton to the helium nucleus. So what that means is we have increased our effective nuclear charge. In other words, that force of attraction that the valence electron experiences towards the nucleus is a lot bigger in helium than it is in hydrogen. Okay, hydrogen is quite a small amount of attraction because there's only 1 proton. In helium, we have 2. And so because we've increased this effective nuclear charge, it means that our valence electrons are going to be pulled closer to the nucleus because they're experiencing that greater force of attraction. They're literally being pulled in by the additional proton. Okay, so it makes sense. As you go from hydrogen to helium, you get a decrease in atomic radius. You get a decrease in atomic radius. In other words, the atom gets smaller, okay? All right, now if we go back to our graph here and look at the next element, we go from helium down here, which has a very small atomic radius, all the way up to lithium. And that's a huge jump, okay? We've essentially, let me just get rid of hydrogen for a second here. We've essentially gone from about 10 picometers for helium to what? 65-ish for lithium. That's a huge jump, okay? So let's just think about this. Again, I get rid of hydrogen for 1 second because we don't need that. We know helium has 2 protons, and if we look at lithium on the periodic table, you'll see lithium has 3 protons. Okay, so based on what we just talked about in terms of hydrogen and helium, you would think, if anything, if you're adding an additional proton, okay, to the nucleus of the lithium atom, this effective nuclear charge is going to be even stronger. And so you'd think the valence electron is going to be pulled in even more. However, we have to also remember here that when you look at lithium on the periodic table, Okay, lithium is in the second period. So if we actually draw our Bohr model for lithium, we have 3 protons. I'm going to make the nucleus a little bit bigger. Okay. We have 1 electron, 2 electrons, and we have our 3rd electron out here. So we've gone to another energy shell, right? Another energy level. When we were looking at helium, we just had 1 energy level, all right? Or you'll hear it also referred to as 1 shell, 1 energy level, that's it. By the time we get to lithium now, this is lithium, we have 2 energy levels or 2 shells. Okay, which means when we look at the distance between the valence electron, which remember is this, valence is the furthest electron away from the nucleus. When we look at this distance here, it's huge compared to helium because we've literally jumped up to a new energy level. Okay, so as we go from helium to lithium, we get an increase in atomic radius. Now, the other thing that's going on here, and I'll do this in a slightly different color, if I just get rid of this atomic radius. The other thing we have to remember is we have the valence electron, which is here, and we have these inner electrons, 1, 2. Okay, so these green ones here are our inner electrons. The other thing is electrons are negatively charged. So the more electrons we add, we also get what's called electron shielding, or we get what's called electron to electron repulsion. In other words, those electrons, because they have the same charge, they push each other away. And so because they push each other away, the valence electron ends up being further and further away from the nucleus. Okay. Now with lithium, we only have 2 inner electrons or 2 shielding electrons. So this effect isn't huge, okay? But as you start to go down further in group 1, this effect of electron shielding or electron-electron repulsion becomes more and more prominent. The main situation or the main cause of lithium's atomic radius being so much bigger than helium is because we've got an additional energy level being added, okay? Now, if we look at what's going on from, back to our graph here, from lithium to neon, you hopefully, if you think about what we spoke about between hydrogen and helium, will be able to fill in the gaps to see what's going on there. Because remember, each time we start with lithium and go across the period all the way to neon, so from lithium all the way to neon, we are increasing the number of protons. And so therefore, we are increasing the effective nuclear charge. In other words, the valence electrons are feeling a stronger and stronger force of attraction towards the nucleus. And so the overall result of that is going to be, we get a decrease in atomic radius. In other words, the atom gets smaller and smaller because the electrons are being pulled closer and closer into neon. And then it shouldn't be any surprise to you that by the time we get up to sodium up here, we get a huge jump again in atomic radius. Well, why do we get that huge jump? Because by the time we get to sodium, we're now starting the 3rd period, right, or i.e. the 3rd energy level. So we're now becoming further and further away from the nucleus. And you'll see this trend repeats again, okay, as you go down, or rather across period 3, you get a decrease in atomic radius because you're increasing the effective nuclear charge, the electrons are getting pulled closer and closer. But then when you start the new period up here, the 4th period, you get this huge jump again because you've now entered a new energy level. Okay, so hopefully that is helpful.